Today's notes are on accuracy, precision, and Sig Figs. First of all, accuracy is how correct a measurement is compared to an accepted standard. So an inaccurate measuring instrument can be made more accurate by calibrating it. What does that mean? Well, an example is on a balance, you turn the knob to zero it out when there's no weight on it. That's calibrating it. If you think about it as a dartboard, if we have our dartboard here and we're aiming for a bullseye, an accurate thrower will hit all of their darts in that bullseye. In contrast to accuracy is precision. Precision is how repeatable a measurement is. You cannot change the precision of a measuring instrument. And what determines the precision of a measuring instrument is the number of tick marks between each increment. So the more tick marks, the more precise a measuring instrument is. So where our dartboard was used in accuracy, if we draw another dartboard, in precision, we can have a very precise but inaccurate measurement or dart thrower where they throw the darts in pretty much the exact same location all 3 times, but it's nowhere near the bullseye that they were aiming for. Proper measuring technique, when you read the measuring instrument, means that a valid measurement includes all the certain digits and one estimated digit. That estimated digit should be equal to 1/10 of the value of the smallest tick marks. So you always can go one place further than the tick marks tell you. So a certain digit is a digit that corresponds to a tick mark on the measuring instrument. This brings us to significant figures. Significant figures are used to indicate the precision of a measurement. It means the more sig figs a measurement has, the more precise the measuring device that was used. So what is a sig fig? Well, it's all the certain digits plus one estimated digit in a measurement. So by looking at a number, how can you tell how many sig figs there are? Well, first thing you do, first rule is all non-zero digits. All non-zero digits are significant. So for example, if I have 413, there's one non-zero, a second non-zero, and a third non-zero. That means that I have 3 sig figs. If I have 413.5, again I have one non-zero, a second non-zero, a third non-zero, and a fourth non-zero. So that means I have 4 sig figs. Rule number 2 is that zeros between non-zero digits are significant. So for example, 509.35. Well, we know that all non-zeros are significant. So all of these are significant right away because that was from rule number 1. Now this 0 here is between 2 non-zero digits. It's between a 5 and a 9, so that's between 2 non-zeros. That makes it significant as well. So now how many numbers did I underline? 1, 2, 3, 4, 5. So that means that 509.35 has 5 sig figs. Let's try another example. 7,003. Well, we have a 7 and a 3, which apply to rule number 1 of our non-zeros being significant. And these 2 zeros are between the 7 and the 3, which also makes them significant, giving us 4 sig figs. Rule number 3. Zeros to the left of the first non-zero digit are not significant. It's very important. They are not significant. That's to the left of the first non-zero. So for example, 0.0013. Well, our first non-zero is right here. These 3 are to the left of that first non-zero. That makes these not significant. No, they are not significant. So our only significant digits are the 1 and the 3, giving me 2 sig figs. Let's try another example. 0.0902. Where's your first non-zero? It's the 9. So anything to the left of the 9, right here, is not significant. Okay, and our 2 we know is significant as well, because it's back to rule number 1 of non-zeros being significant. This 0 applies to rule number 2. It is sandwiched between 2 non-zeros, making it significant. So that gives us 3 sig figs. Rule number 4. Zeros to the right of non-zero digits are only significant if there is a decimal point written. So only if that decimal point is recorded are those zeros significant. So for example, 1,000. We have a 1 here. These zeros are to the right of that non-zero. There is no decimal point that is written right here, which means these zeros are not significant, which gives us 1 sig fig. In this case here, we have a decimal point written. So we still have our first non-zero here. These zeros, now they're to the right of the last non-zero, but there is a decimal point written right here, which means that these zeros are significant. So let's underline all of them, and that gives me 4 sig figs. Our last example, or another example, is 53.590. So our last non-zero is this 9. This 0 is to the right of the last of the 9, and there is a decimal point that makes it significant, which gives us 5 sig figs. And our final example. How many sig figs are in here? Okay. Our last non-zero is this 7. These zeros are to the left of the first non-zero, our 4, makes them, these guys are not significant. This is to the right of our last non-zero. There is a decimal, so that is significant. Our 6 is by default significant because it's a non-zero. And this 0 is sandwiched between 2 non-zeros, making it significant as well. So that gives us 1, 2, 3, 4, 5 sig figs. Now there are going to be many times in this class that you are doing calculations with measurements or calculations with sig figs. So we need to know how sig figs are affected by calculations. So the idea is that the answer to a calculation should not show more precision than the measuring device that was used to take that measurement. So to ensure this, we need to round our answers to calculations to the appropriate amount, or the proper amount of sig figs. There's different rules with different types of calculations. So we'll start out with addition and subtraction. In addition and subtraction, you round the answer to the same number of decimal places. Decimal places here is the important part, as the measurement with the least number of decimal places. So if I have two numbers, 10.34 and 1.5. This one has 2 decimals. This number here, this measurement here, only has 1 decimal. So I need to round my answer to the least number of decimals. That means I round it to 1 decimal. When I punch this into my calculator, though, I get 11.84. But that means I need to round to 1, like I said before, we need to round to 1 decimal place. So that means I'm rounding to this first decimal place of the 8. So if I round it to the 8, because this number here after the 8 is smaller than 5, then the 8 stays the same, and I end up with 11.8. Let's try another example. We're moving on to multiplication and division. All right, so for multiplication and division, I round my answer to the same number of sig figs as the measurement with the least number of sig figs. So in multiplication and division, instead of looking at numbers of decimals, we need to determine the number of sig figs. And we still want the least number of sig figs. So for example, 3 times 5. Well, we know that 3 times 5, when we punch it into our calculators, gives us 15. But we need to round that answer to the same number of was the least number of sig figs. Well, 3, this is 1 sig fig. 5, that's also 1 sig fig. That means my answer can only have 1 sig fig. But my calculator answer of 15 has 2 sig figs in it. So that means I have to round it to the first sig fig. That's the largest number. So here, because the number after the 1 is a 5, that means I round this up, because that means I round up. That means my answer rounded to the correct number of sig figs is 20.